But close. He's going to be talking about slosh in vehicle motors as used in space. He has his master's degree and he's currently working on his PhD in mechanical and aerospace. He's working on a very exciting topic and actually working in the launch services program. The launch services program at NASA are one of the companies that's actually provided part of the funding that was used for his research for his flight article. So we're very excited about hearing his research. Before we get started, I want to make just a couple of announcements. First thing, so everybody's aware, is between each of the sessions, they are pulling raffle prize tickets. So after the session, there's a board in the lobby that has the number, so you can swing by there and check throughout the day to see if you won a raffle prize. We also have some additional t-shirts and patches, if you're interested, that are still available for sale. And then in the vendor room, Aerospace Specialties vendor is going to have to leave today at noon. So if you were looking to buy something from them, you'll have to get in there before noon. So with that, let me turn it over to Gabriel.
Thank
you very much.
Appreciate it. Hi, everybody. Well, we're going to be talking today about a good experiment that we're performing right now up in the space station. So, liquid sloshing in microgravity. First of all, we're going to make a brief introduction into why we want to study liquid propellant slosh, some results that we got before making this experiment, what are the goals and the objectives, and present our experiment itself. Why do we want to go for and study these propellants? Pretty much every single or most of the rockets that use liquid propellants have different shapes of tanks. You know, you can even see the Delta IV that use liquid propellants. And these tanks are massive. They have percentages of mass with respect to the rocket, that of liquid propellant with respect to the rocket, that are considerable. So the dynamics of the rocket is highly affected by the fluid motion inside the tanks. So why is all this trend happening? Why do we want to study the behavior of the fluid inside the tanks now in 2014? Well, what happened is back in 2005, Dave, correct me if I'm wrong, 2005 or 2006 was it? A Delta IV launch was postponed and was scrubbed a few hours before the launch because two computational models that NASA used for 40 years to predict the behavior of the fluid inside the tanks were giving different results. So the guys, the mission planners, had these two tools that have been developed 40, 50 years ago. One was a 2D CFD, pseudo CFD case analytical analysis, and then the other one was a full 3D analysis, but still was based on equations and basic physics, but they have never been correlated with real data in microgravity. So the Delta IV was supposed to launch and make a few maneuvers. One of the models said, you know, you're okay to make those maneuvers, and the other one said, well, it's going to be awfully close to a vent. What happens when the rocket is turning or is making maneuvers up in stage, in upper stages, it's making a maneuver, say to change attitude, to rotate, or to make a roll for evening out the boiling of the propellant. Sometimes you have to relieve pressure inside the tank because of boil off. The cryogenic propellant boils off and pressure increases in the tank. That means you have to relieve that pressure. When you relieve that pressure, if your fluid is near the vent and you get sucked through the vent some fluid, you will be, not fluid, let's call it liquid. You don't want to be venting off liquid. If you vent off liquid, it's not a good thing. You can get it blocked, you're losing propellant, and it could lead to unstable conditions. So one of the models said, yeah, you're good, you can do it. You're fine, you're perfectly good to launch. And then the other one said, well, not really. So that's why the folks from NASA, they had to scrub the launch last minute. And they said, well, how do we calculate this? These two models. Okay, so how do they correlate to each other, and how do they correlate to reality? There's no data from that. They have never been correlated to reality. That's why they came to Florida Tech for some help with that. And that's when we started back in 2009, 8 with Slosh, probably. In the beginning, it started with 1D simulations in one gravity, basically one tank moving back and forth and trying to understand the behavior of the fluid. Then we jumped into rotational rigs, and we jumped into zero-G flights. But then the ultimate goal was to get long-term data or long-duration data, because in a zero-G flight you can only get 30 seconds, 40 seconds of data, no more than that when the parabola is in the but that's not good enough if you want to plan a long-term mission or longer mission or longer maneuver of the station. So we developed some tools that were giving us already pretty good results in a 1G environment, but still needed to be correlated, right? Why did we want to do it on the ISS? Well, the ISS is a controlled environment, it's a laboratory, and we could use the spheres. What are the spheres? The spheres are these satellites that are self-propelled by CO2. They have 12 thrusters each, so they can move in all 6 degrees of freedom. And they provide a platform for developers, for guest scientists, that's how it's called. These spheres are a program developed by MIT originally, and now NASA Ames is the owner of the program. And they've been up in station for 10 years, so it's fairly proven and well developed. This would give us the first long duration database of liquid in microgravity. So what do we want to do? Acquire long duration, low gravity, call it microgravity, slush data to calibrate CFD models. We want to grab those models original and plug the data that we get from this, compare it, and validate these models. That's the ultimate goal of this project. Of course, it's got a lot of commercial implications, right? One is from the safety standpoint. NASA needs to be able to tell the companies, mostly now that it has outsourced pretty much everything, and it's going to commercial companies. They want to be able to tell, you're safe to launch, or you're completely safe to do this or not. Before, I think it was more constrained to a fewer launch vehicles. Now everybody's doing their own, and it's kind of starting to branch out, and this thing will become more general. So they need a good way to assess the safety of operation. On the other hand, this is great commercial opportunity for LSP, because they can sell this quite well, I think, for data analysis. So how do we want to do it? We want to use the spheres, these satellites, to propel our experiment, to move it around. And meanwhile, we have a data collection system that will take pictures of the fluid with 2 different cameras in 2 different positions, so stereo imaging, and collect inertial data, so accelerations and gyroscopes. After that, we'll benchmark the solutions. How does it look like? Well, our experiment looks like that. It's kind of odd looking, but you get to gain some love to it after you've dealt with it for a while. We got the 2 spheres, originally developed by MIT, on the sides. These are our data collection systems, out of which the main computer is also part of this. This is the main computer right there, which is called Vertigo. That main computer was also developed by MIT for a different project, and it had an attachment with some optical mounts to do stereo imaging. Well, we removed that completely. We're just using the processor, basically. We included our own data collection system, or Slosh avionics box. That's where we have all our sensors, IMUs, inertial measurement units. We have some cameras that point to the tank in there, And this is a light box that has 2 LED strips on top and bottom. That's what keeps the illumination to a controlled level. And these satellites are connected by a frame that, as you can see, it has a counterweight over there, meaning this whole thing is perfectly balanced. So the CG of the entire system and the center mass of the entire system, even though they differ slightly, they're in the center of the tank. So the tank is a pill-shaped tank with fluid inside. The liquid is water. Basically distilled water with food coloring. That's what it is. So if you see something green that looks nice and looks incredibly scientific, it's actually distilled water with food coloring. So. This is the actual flight unit. We took these pictures before we shipped it up to space. This was back in July, if I'm not mistaken. It was missing just the labels, basically. It was ready for flight. These were pretty much the last pictures we got before it was put in the rocket. How do we make this? These parts are 3D printed. All the light brown parts are 3D printed out of Ultem. Ultem is a material that is a plastic that has great properties for off-gassing, which is critical on station. If it catches on fire, it cannot be creating toxic gases. So every single one of these materials were carefully selected, and 3D printing was what was giving us the greatest flexibility for creating this. And since it's pretty much one of a kind, that's the route that we decided to go. Even the tank is 3D printed. You see that and you're like, how did you 3D print that? It looks transparent. Well, yeah, each one of those tanks is quite a challenge.
What kind of pressures were being run inside that tank?
Just atmospheric.
Just 1 atmosphere?
1 atmosphere, yeah. So we filled it up, we sealed it, that's it. It's going up. We had to run some pressure testing for the certification for safety. So these tanks were run to 1.5 atmospheres, so above relative, right? So above atmosphere. So we actually put 2.5 atmospheres in. So yeah, that was quite a challenge because that requirement came after the design was done and some tanks were built. So we broke a few, basically trying to certify them. The seam was not perfectly glued together. There's a seam in between there. And so yeah, we broke a few that the glue was not perfect. Anyways, our experiment is currently on station. It flew on board Cygnus on early January. I think it was like 8th or 9th of January. That's what it actually looks like in reality. You can see the spheres, you can see the vertigos right there, the avionics boxes, the light box, and the tank is in there. The frame is made of aluminum. The precision of the frame, it was machined to an accuracy of 0.1 grams. So this whole thing was...
So Gabriel, can you maybe, I know you mentioned Cygnus, but I mean, Cygnus is the carrier. Maybe you can tell them just a little bit about the vehicle that Cygnus was on?
Right, yeah, Cygnus is an Antares vehicle. It's an orbital sciences vehicle, and it's got what's the payload capacity? 2,500 pounds, right?
Yeah, it might even be higher than that. I can't remember off.
Yeah, 2,500 pounds, and these missions are under a. I think they're going to launch 8 or 10 different missions. And they're under a resupply contract for the ISS. They're unmanned missions. And Cygnus, basically it's a capsule that gets shipped up, docked to the station, resupplies, and then re-enters, destructive re-entry, basically. It's a garbage disposal for the ISS. So it's a fairly cheap way to send things up. And we actually flew in Orb 1, which was the first commercial resupply mission of Cygnus. So, all right, so let's talk about the slosh experiment itself. We can see different shapes of tanks. We chose the pill shape because that's the most representative to upper stage tanks. Usually we also work with ATK in different projects, so you either have pseudospherical tanks with different curvatures, but most of the times, as soon as you start increasing the capacity of the rocket, the only chance you have is just to stretch it, right? So that's why we chose that pill shape tank that you guys saw. So what maneuvers need to be done or need to be validated? Basically the maneuvers that are going to be executed by the rockets up in station, right? And up in space. So one is the barbecue roll. This maneuver is intended to even out the solar heating on the rocket. If you just leave it there and the sun is hitting it on one side, it will just heat one side and the other one will be extremely cold, right? So the barbecue roll is intended to even out the heating on the entire rocket. So that's a very common maneuver that's made up in upper stage rockets. What happens in 1G, you can see that you get a beautiful distribution of the fluid and going outside, but what happens in 0G? So in 0G, you would see the fluid going towards the outer wall, but then you have waves that start to rotate, and then you have vortices, and it's not that common, that easy to understand to see it. The first time you see it, you're like, yeah, that kind of makes sense, but not really, right? We're so used to 1G that once you put everything in 0G, then your thoughts are completely wrong. Another maneuver is the turn to attitude. Basically, you're flying straight, you have to go that way, you have to rotate your rocket this way and make it go up. So that's a turn to attitude. We basically call that a pitch maneuver. How do we correlate what's dominating the fluid forces? There's different non-dimensional numbers, such as the Weber and Bond numbers, the Reynolds number, the Froude numbers. The ratio of these numbers will give you an insight of what's dominating the fluid behavior. So as you can see, the ratio of the Weber number to the Bond number will give you either if it's gravitational forces what dominate the regime, or it's inertial forces what dominate the regime. What does that mean? If I have a blob of fluid, right? If I push it hard enough, or I have gravitational forces, how big do they have to be for them to start dominating the entire fluid motion? Or, in other sense, is how much acceleration do I have to impose to dominate that fluid motion? And the Reynolds number to Froude number provides an insight of either if it's a gravitational force or viscous regime. And that means what's creating the dissipation in the fluid. It's either the gravity pulling it to one side or the fluid itself trying to reshape and dissipate the energy, right? So how do we apply these? You can't match all the maneuvers that you want to do with all the numbers at the same time. So what we do is we select different matching parameters and matching characteristics for each maneuver. So for the settling thrust maneuver, we're going to match it by the Froude number matching. Why do we use these numbers? Because we're using a tank this small to replicate what happens in a tank that's 5 diameters maybe, and a Delta IV rocket 5.1 diameters and 40 meters tall, right? So with these numbers, we can correlate different sizes. In the pitch to rear end, we basically match rotation rates, and with thermal control maneuvers, so barbecue rolls, we basically match the rotation rate. That's the best thing you can do. So what are the maneuvers that are supposed to be done on the ISS? Well, you have, first of all, you simulate an engine shutdown. You are thrusting, you turn it off and you let it coast. So first of all, you're accelerating. Your fluid is going to go one way. You stop the engine, you let it coast, and then you fire it backwards. So what happens with the fluid inside the tank? The turn to additive is something similar, but then you have to just rotate it, right? And the thermal roll will be just rolling along its longitudinal axis, correct? What do we want to achieve for initial conditions? We need something, and this is actually what we're dealing with now. Yesterday we had an operating session, and we came across this. So I'll talk about this in a few minutes because this is important, and now it's taken a whole new spin about this. We want to be able to generate an initial condition that's easy to replicate and model in a computer, right? That's not easy to do it. If you think about in gravity, in a 1G environment, yeah, it's fairly easy. You put it in a position, but in 0G, it's quite challenging to get the fluid to either one side or to have very few bubbles. Because what you see is the fluid starts to get bubbly. And all these bubbles are inconsistencies in your domain, basically. So how do we generate that in a computer? It's extremely hard. So these are results from a CFD model that we ran, and this was pre-launch, right? So this hasn't been validated yet. These were the preliminary studies we were doing with CFD ourselves. So now we're going to jump into the fun part. Each test session lasts for about between 5 to 7 hours. It takes about an hour to set it up, the entire hardware, about an hour and a half to shut it down and download all the data, because all the data is stored in the computers. So we download all that stuff, we pass it to literally a thumb drive, and we plug it into a computer and we download it, we retrieve it. We're talking about 10 to 15 gigabytes of data, and it's not like downloading it from a torrent, right? So you're downloading it from the ISS. So this is in chunks of files. So the data download process is quite long and tedious. We have, for each test session that we get, we can run between 10 and 15 different tests, individual test maneuvers. And how are they doing? First, we run a settling maneuver. Then we run either the passive thermal controls of the barbecue roll, or we either run the pitch to reorient or the translations, right? So here we had the first, the checkout session, which is a session that allows us to assess the integrity of the hardware. Basically, first time they open it up in space, our biggest fear was to see that bag, that triple CTB bag that contains the experiment, all green. That was our biggest fear, basically. So when they brought out the bag, the white bag, and it was still white, it was a relief, I gotta tell you. But we had a minor component down. It's just the tip of one of the boxes that broke off during launch. Well, either during launch or someone broke it before putting it in the rocket. We don't know that, but nothing major at all. The hardware worked perfectly. The checkout session was intended to test the functionality and then do thruster characterization, meaning how much thrust does each thruster put into the system, because it's fairly defined, but it's not for sure, right? Because if you slightly cover the thruster, you don't know how much it's putting, right?
Do the mission specialists work with this system prior to going to orbit, or they see it for the first time up there?
Well, they were trained with some mock-ups, basically, but yeah. But yeah, the crew members were the first time they were seeing this. They have worked with the spheres, but not with the experiment itself. they got some training, but it basically pretty much they sent them an email. Yeah, it's a long, tedious process of procedures, writing documents, and we've been through all that stuff. So this was a fun moment that I wanted to share with you, to give you an insight of how everything happened. You know, when they were putting the experiment away, we asked the crew members to start playing with the tank before putting it away. So they did right in front of the camera, and this was a great moment. And too bad we don't have the audio, but you can hear the people from the ground saying, "I haven't seen Rick," that crew member right there, so happy for a long time. So even, you know, a minor rotation will make it split in two, and pretty much evenly, right? Some of these things are just eye-opening, right? It's a minute rotation, it will just make it split in two perfectly even. As you can see, there's a lot of bubbles there, and that's actually, from this video we got so much feedback, because we got all the data back. But from this video, we got so much information by just looking at it over and over on what generates the bubbles, how can we get a clean domain, and that's what we wanted for our Science 1 session yesterday, basically. So you can see that the water is connected by many tiny blobs. So basically, the surface tension is dominating completely the fluid. And when we downloaded the data from this session, which was the first time we ever operated that, I think that container, if I haven't heard wrong, that's the largest container on the ISS, you know, that's in there. So, and when we downloaded the data, we realized that we had a lot of bubbles. We couldn't really do much with it. So for our session 1, our Science 1 session, so the first one where we expect to deliver, that's the difference between a checkout session and a science session. From the checkout session, you have to test it, make sure everything's good. For science session, they expect deliverables, right? So the contract says you need to give us this after your Science 1, Science 2 session. So that's the only difference, right? That's the wording behind it. So for our science session, that actually we ran yesterday, so it was a quite long day. We started at 5 in the morning. The main science objective was to reduce the bubble count to create a stable and easy to model condition. After seeing the checkout section, it was just horrible. We had bubbles everywhere. So that was our main science session. Originally, we were supposed to do the barbecue rolls, pitch maneuvers, rotations. We're like, yeah, we can do that. It's easy. We did it in the checkout session. We can do it super easy. But now what we need to do is we need to extract the science. So actually LSP is now changing their idea, and they say, you know what? Let's just work on getting a good stable condition, initial condition that we can give the guys that plug into their models, and that's what we're aiming for right now. So Science 1 was mainly achieving that. So we got also the crew members to start playing with it, because we realized that the spheres may not have the thrust enough to break the surface tension and make, again, going back to the non-dimensional numbers, to make the inertial forces dominate over the surface tension, pretty much. So we said, all right, so we'll just have the crew member play with it until they can reach a stable condition with low bubbles, and then we execute our maneuvers. So this is what happened yesterday. We had, too bad it's kind of dark there, but we had Rick Mastracchio play with it for quite a while, and we told them, you know, we know you're a procedures guy. We know that you are, you're just there to do what you're told, but just do whatever you like with it. This is what we need, play with it. And he got some great results, you know. He managed to find a way to stabilize the fluid in a great way. So we're extremely excited to see what comes out of This is a spheres-driven maneuver. As you can see, it was still and it starts to move by itself. This has the light box on. We made them run a few tests with the light box off, as you can see, with the cover off, so they could see the tank and they could see what they were doing. So this is right now what's going on. We need to be aiming for another science session probably in about a month with a tank with a different fill level. This is a 40% fill level tank. We're aiming for one with a 20% fill level. What time is it? 10:17. Okay, so I'm still got about 10 more minutes. So basically, we have, as I was just saying, we have 20% fill level tank, a 40% fill level tank. We also have a solid mass replicator, which the intent of that one is it's just a tank with a thicker outer shell that represents the mass inside the 40% tank. In the future, the idea is to correlate and say, all right, we want to move our vehicle this way. With fluid, it responds this way. Without the fluid, or with the exact same mass but no fluid interaction, it acts this way. That way, we can relate those and make a control system that accounts for the fluid sloshing behavior inside the tank. Applying the same thrust or the same excitation to our vehicle. What's the difference in response with fluid? Without fluid, can we model it, and can we include that in a navigational system? That's the ultimate goal that we have. That's why we have that third tank that's called solid mass replicator, with an exact mass of the amount of fluid that's in there, but evenly distributed around the surface. It's basically a thicker wall. We got 3 test sessions, and right now we are negotiating with LSP, possibly getting 6 more, but this is unofficial, so maybe not in the video. The slosh experiment right now is being handled by Kennedy Space Center and Florida Tech, but after these 3 test sessions, it's going to be handled to NASA Ames Research Center, and they're going to be the owners of this experiment. And the folks at KSC are the ones doing all the data analysis and providing us all the feedback on how to make these maneuvers and optimize this. So, quick summary. We started with just a rotating rig with a tank stuck on it and trying to see how everything behaved in a 1G environment, spinning around. We got some nice pictures, we simulated them. Then we did some 0G flight. We got some good agreement with our simulations. Now we're running in the space station, and we're analyzing right now what's our agreement and how good our models were. So this is where we are right now. Any questions?
What kind of software are you using for the CFD analysis? Is that private or what?
We use either Fluent or Flow3D, but that's us, basically. KSC has, or NASA has their own.
Are there large modifications to the model when you actually start dealing with LOX or liquid hydrogen as opposed to water?
Well, yeah, absolutely. You have to change the fluid parameters, but the thing is, we have to start with something.
Right.
So, from a safety perspective, water was the only thing we could put in there, right? Because it's a space station, so forget about using actual propellant inside the station, which the safety people will just scream at you and probably hunt you down or something like that. So yeah, for now we're just doing water. I know there's, and Dave may be the person to ask about that. I think there's a project that's intended to put some cryo tanks up there and do some testing. Or there's an idea for that in LSP?
Yeah, it's quite a ways off though.
Yeah, but it's an idea. They're trying to go with some cryo tanks, put them in space and make some measurements and extract some data out of them. That's the ultimate goal. Yeah.
You were talking about initial conditions. If you were just to allow the fluid to sit, it would of course adhere to the walls. With the cameras, do they see the structures, like you're talking about a barbecue roll maneuver, how it adheres to the walls and the structures and vortices will form? Will the cameras be able to see through that fluid to see the structures on the inside of the tank? Or will you have to somehow cause a split in the cohesiveness of the fluid?
No, you can see that. You can see that with the cameras. That's why we got stereo cameras, 2 cameras. The initial conditions for these, it's mostly, I don't want to say qualitative, but because you get some good positioning feedback, but you have to go and measure the images basically and see what your initial condition is, where the fluid is. But yeah, you don't have to make a deeper analysis of what it is. Of course, we would like to have, maybe for a future version, probably either 3D imaging, like 2 different cameras with 3D imaging, or something that could literally create a 3D model of the entire fluid and give you an completely accurate representation of what's in there. For now, we're testing the technology. We got 2 2D images, and for now that's good. But what can be done further to improve it? There's a lot that can be done. Yes.
And so you're talking about mostly rocket maneuvers. Is there any future plans to apply to satellite maneuvers?
Oh yeah,
So
absolutely,
looking at the
absolutely. Anything that has a propellant tank. Anything that has a propellant tank can be applied. Yeah, absolutely.
Are you sharing your results anyplace online for people to follow up?
Well, right now KSC is not. Eventually, I think we'll make some publications. For now, this is ITAR restricted, so it's being handled quite secretly in that sense. But we'll see where this data. That's why I cannot show any data, because I can't even see it. I'm not a U.S. citizen, so I can't even see it. So, but yeah, eventually, I think once the analysis is done and the post-processing is done completely and the post-analysis is done, I think the intent of LSP and KSC is to open this to the scientific community. Yeah, I think so. That would be a good way to go.
You said you wanted to simulate the engine cutoff and restart. It's going to slosh. How are you going to simulate that on that experiment setup, the apparatus you have up there? Like, I understand it can rotate and move, but how are you going to accelerate and stop it?
Yep.
You can do that?
Yep.
There's enough space on the ISS to do that?
Yep.
Just down that hallway?
Well, depends on what you want to do. This is quite slow. So the amount of thrust you get out of each one of those thrusts is 0.1 newtons.
Yeah.
So you got, say, up to 4 thrusters. So you get 0.4 newtons. It's a 23 kilogram experiment. So everything moves quite slowly. That's why the spheres-driven maneuvers, we have a test volume that we are allowed to work on. That's 2 meters by 2 meters by 1.5 meters. So that's where we can move around. And and the idea of this session was also to test out how much farther we could go with the crew member, because the crew member can impose higher accelerations on the system.
Right.
So yeah, that's how we simulate it. We basically have a motion of 1 meter in total, because all that matters is acceleration, right? It's not the velocity. You don't have to shoot it at 13,000 miles an hour and then slow it down to 10,000 miles an hour, right? So it's all acceleration. So if you just push it a little bit and then let it coast and stop it, that would be your simulated maneuver. And with the non-dimensional numbers, you can scale it to whatever your real condition is.
Will later focus be primarily on cryo propellants, non-cryo live propellants, or mono propellants?
Either. Yep.
Is there a priority as far as of interest? Or?
We don't have a priority set. if you have anything that you want to study, talk to us specifically. So yeah, right now there's not a priority. We're still working with this, but we're open for any kind of suggestions and different work.
Well, I mean, Gabriel, isn't it kind of, this first experiment was really to see if
Proof
you
of
could
concept.
achieve it, a proof of concept, could you make it all the way to a flight article? And you wanted to use, frankly, the most benign fluid around, distilled water. So now that you've proven that, I think it makes sense that, now the applications will come now that the technique has been proved.
Yep. Good. Any more questions? I think we just ended.
All right.
Yeah, 10:30. So
Yeah.
I gave you 15 minutes
Yeah,
plus.
perfect.